Day 19 of the TryHackMe Advent of Cyber is upon us, and in this video, we're going to take a look at the daily task. I'm logged into tryhackme.com/Christmas in the room for Advent of Cyber 4 2022, and in this video, we're going to be diving into some hardware hacking. If you aren't familiar, that is the task for today, and my goodness, I'm a little bit nervous because, look, I don't know anything about hardware hacking, or just, I don't know, all that stuff. So we're going to dive in. I'll hop over to my computer screen and let's explore what is in front of us here for day 19 hardware hacking with TryHackMe's Advent of Cyber. Okay, so just a heads up, I am going to do a whole lot of reading so that we can get actual context and know what we're doing here for this task, because again, this is a little bit new to me and I'm going to learn something new just like everyone tuning in. So let's dive into it. Let's see, hardware hacking day 19, wiggles go burr. All right, I have gone ahead and started the machine, so that's running up here with a little bit of time. Note they have a specific statement here. The VM that we'll use in this task takes approximately 8 minutes to start, and that is why, hey, we suggest you start the machine now, have it ready by the time you get to the practical element of the task. With that said, we are going to be spying on Santa, or learning how this is going down. Elf McSkitty was doing a regular sweep of Santa's workshop when he discovered a hardware implant. The implant has a web camera attached to a microprocessor and another chip. It seems like someone was planning something malicious. We must try to understand what this implant was trying to do. We'll deal with the microprocessor and the web camera in future tasks. For now, let's just get the ball rolling, try to uncover what the other chip is being used for. So a couple learning objectives here, what we're going to be getting into. How is data sent in electrical wires to low-level hardware? How hardware communication protocols work, what they're up to, what they are, and how to analyze hardware communication protocols. Additionally, we'll be reading USART data from a logic capture, USART, I don't know how people say that. Anyway, welcome to the Matrix. Hardware hacking is often shrouded in mystery and seen as a super complex topic. That's for sure. I know nothing about it. While there are a lot of in-depth, complicated, and complex hardware hacking components, getting our feet wet is actually pretty simple. Computers today are incredibly powerful. This allows them to build additional features and safety measures into the communication protocols to ensure that messages are transmitted reliably. Think about the Transmission Control Protocol, or TCP, which has multiple redundancies in place. It even sends 3 full packets just to start its communication. In the world of microchips, we don't often have this luxury. To make sure our communication protocols are as efficient as possible, we need to keep them as simple as possible. To do that, we need to enter the world of zeros and ones. This then begs the question, how does hardware take electricity and generate signals? In this task, we'll focus on digital communication. For hardware communication, we use a device called a logic analyzer to analyze the signals. This device can be connected to the actual electrical wires that are used for communication between two devices that will capture and interpret the signals being sent. In this task, we'll use a logic analyzer to determine the communication between two devices in the rogue implant. Now we're diving into the electrical heartbeat. Back to our question, if we have electricity, how can we generate a digital signal? The approach most hardware components take is to simply turn the power on and off. If the power is on, we're transmitting a digital 1. If the power is off, we're transmitting a digital 0. We call these ones and zeros bits. To perform communication, we simply turn the power on and off in a specific sequence to transmit a bunch of zeros and ones. If we send 8 bits, then we're sending a single byte. And voila! We've just performed digital hardware communication. These are the wonderfully squiggly lines that you would see on a logic analyzer. And here's a picture of a Logic 2. Looks like a logic analyzer that we might be able to play with. And you can see sort of this up and down here of the signals, the zeros and ones that are sent. Remember, those zeros and ones are just bits, but when you put them together in sequence, especially even 8 bits, then you get a byte. We can transmit text data by using the ASCII table. If you aren't familiar, the ASCII table is kind of the set of characters that can be represented in at least numeric form, kind of 0 to 255 in base 10, or decimal, the same way that we as humans and people count on our fingers or whatever, 0 through 9, base 10. Remember, in binary, we're working in base 2, you just have the values 0 and 1, much like our bits here, but the ASCII table, and it's oftentimes representing with different text or formats of data. It could also be presented in hex, or you might see even other base 16, again being hexadecimal there, different formats of the data. In this case, we do need to boil it down to the bits, the zeros and ones, the ones and zeros, all the strings here that we'll end up using. Sending the binary representation of each character, remember that's the zeros and ones, we can transmit data. However, it actually isn't just that simple. If we wanted zero effort in our communication, we would need an electrical wire for every single 0 or 1 that we wanted to transmit. Considering that a single character is just 1 byte of data and therefore 8 digital wires, or electric wires, this can be a mess of wires stacking up really fast. So to make this more efficient, we need to use fewer wires, and then those have hardware chips. Both hardware chips will agree to use a specific digital protocol and a configuration that will be used standard to transmit data. So let's take a look at some of the most common protocols and how they work to send data while still reducing the number of wires that are needed. First things first, we have USART or USART, you call it whatever you want. This is the Universal Synchronous or Asynchronous Receiver and Transmitter Communication, or as it's better known, serial communication. And it's a protocol that uses 2 wires. One wire is used to transmit, or TX as a sort of shorthand notation, transmit data from device A to device B. And the other wire is used to receive, or RX as that shorthand, receive data on device A from device B. In essence, we connect the transmit port from one device to the receive port from the other device, and vice versa. What's interesting about this protocol is that there is no clock line that synchronizes the communication between these 2 devices. Without a clock, the devices have to agree to the configuration of the communication, such as the following. This breaks down to communication speed, also called the baud rate or the bit rate, and it dictates how fast bytes of data can be sent. When both devices agree to a specific rate, that tells them how fast it should sample the data to get accurate communication. While there are fixed standards for baud rates, devices can choose to really use any rate, as long as both devices support it, as long as it's in agreement with the other device it's communicating with. Next, you have bits per transmission. This is normally set to 8 bits, which makes a byte, but it can be configured to something else, such as 16 bits. You also have stop and start bits. Since there is no clock, one device has to send a signal to the other device before it can send or end a data transmission. It's really initiating the conversation. The configuration of the start and stop bits dictate how this is done. And finally, you have parity bits. Since there can be errors in the communication, parity bits can be used to detect and correct such errors in the transmission. Once the 2 devices agree on the configuration of the serial lines, they can now communicate with each other. A single transmission is shown in the diagram below on how the ASCII character of S would be transmitted. So check it out. In this diagram, you can see 0x53 at the very, very bottom, and that's equal to the ASCII S character. Bear in mind that 0x is the hex representation. It's denoting that it's using base 16 or hexadecimal to refer to this, but the ones and zeros just above it, as you can tell, there are 8 values there, 11001010, and those are the bits that's sending this data, representation of the ASCII S character, what could be represented in base 16 as hex 53 or base 2, 11001010. And you can see the start bit is sent, and this little line here is kind of denoting the communications. Starting with 0, and then some other things jumping up in that little square wave here of the ones where that power is on to send the signal. And we do the very, very same, all through the string of ones and zeros. And then you have a stop bit. Now, there are a couple of caveats with this. The devices don't really have a way to determine if the other device is ready for communication. To solve this, some USART communications will use 2 additional lines called the clear to send and request to send to communicate with the other device whether or not it's ready to receive or ready to transmit. Furthermore, to agree upon what voltage level is a binary 1 or a 0, a third wire called ground, or GND, is required to allow the devices to have the same voltage reference. However, despite all of this, I know we're adding in a couple other complications where you've got all this stuff going for the communication to begin with, and then you've got clear to send and request to send and ground. Well, hey, USART is still an incredibly popular protocol in microprocessors due to its simplicity. And at the end of the day, that's what we're going to end up finding. As we dig more and more into this hardware work, it's still going to be just ones and zeros. It's still going to be just data, and we'll have to keep it simple. So next up is SPI, or SPI, as some folks might refer to it as, I don't know. The Serial Peripheral Interface, or SPI communication protocol, is mainly used for communication between microprocessors and small peripherals, such as a sensor or an SD card. While USART communication has the clock built into the transfer, transmit, and receive lines, SPI uses a separate clock wire. Now, separating the clock, SCK, from the data in all caps, that data line and keeping those two separate between the clock and the data allows for synchronous communication, which is faster and more reliable. The trade-off, though, is that you're adding an additional wire, but you do gain speed and a little bit of reliability. An example of the same S ASCII character being transmitted using SPI or SPI is shown right below. You'll note you have the very same data line, but the clock is just here. And you can see it's a little up and down constant square wave that's just the pulse or the heartbeat of the data being sent. The clock line tells the receiving device exactly when it needs to read the data line. Two-way communication is also possible, but quite a bit more complex than just serial communication. Essentially, one of the devices is labeled as the controller. This is the only device that's allowed to send clock signals. They are the mastermind here. All other devices become secondary devices that must follow the controller's clock signal to transmit data back. It needs to know what the marching orders are, when and where. If two-way communication is used, instead of having a single data line, two lines are used, namely peripheral in, controller out, or PICO, PICO, which means communication is sent from the controller, and peripheral out, controller in, POCI, Pocky, I don't know, like the chocolate sticks. That means communication is sent from the secondary device back to the controller. Using this, the controller sends a clock signal and command out to the device using the PICO line, peripheral in, controller out, and then keeping the clock signal, the controller receives back on the PICO line, as shown in the diagram below. So note these other connections at the top here. Here's the clock, here's peripheral in, controller out, controller in, and you have your SCK clock from the controller, again sending that pulse, that heartbeat, the cadence of the data being sent, and PICO, peripheral in, controller out, and then POCI, peripheral out, controller in. Notice we're still getting now sent this ASCII S in those bits, zeros and ones, and then a little bit of a response here, ASCII F. There's one additional change that needs to be made, though. While there can only be one controller, there can be multiple secondary devices. To save wires and ports, all devices can use the same SCK, PICO, and POCI lines. PICO and POCI. A fourth wire, called the chip select wire, is used to distinguish the device that the communication is meant for. The controller can use this line to indicate the specific device that it wants to communicate with, it. All is shown in the diagram below. You've got the controller, SCK again, PICO, POCI, and now CS1, CS2, and CSN, for however many other peripheral devices you might be communicating with through that controller. SPI communication is a fair bit more complex than USART, but having a dedicated clock line increases the speed at which we can communicate and improves reliability. Yeah, I'd consider that an upgrade, personally. I think having that heartbeat in that frequency, kind of the cadence of data being sent where and when, is important in my mind. Next up, we have I2C. The Inter-Integrated Circuit, or I2C communication protocol, was created to deal with the drawbacks of both USART and SPI communication protocols. Because USART is asynchronous and has the clock built into the transmit and receive lines, that means that both devices have to agree ahead of time on the configuration of the communication. Remember, that's that baud rate. Furthermore, speeds are reduced to ensure communication remains reliable. On the other hand, while SPI is faster and more reliable, it requires many more wires for communication, and every single additional peripheral requires another chip select wire. So I2C attempts to solve these problems. Similar to USART, I2C only makes use of two lines for communication. I2C uses a serial data or SDA line and a serial clock or SCL line for communication. However, instead of using this chip select wire to determine which peripheral is being communicated to, I2C uses an address signal that is sent on the SDA or the serial data line. This address tells all controllers and peripherals which device is trying to communicate and to which device it's trying to communicate to. Once that signal is sent, a data signal can be used to send the actual communication, the payload, what is included within that conversation. Now, to notify other controllers and peripherals that this communication is taking place, and to prevent these devices from talking over each other, a start and stop signal is used. Each device can monitor these start and stop signals to determine if the lines are busy with communication. An example of this data transmission is shown below. Remember, you have our SDA, or our serial data line, and SCL, our serial clock. Now note, hey, we have a start condition that goes low, right before the SCL, or the clock here, and then the 7 address bits that might want to be sent, and then you have an acknowledgement that tells, hey, okay, we know this is happening. It indicates that the address peripheral either did not respond or was unable to process the request. After that address is sent alongside and in cadence with the clock, it then will send the data, again on that serial data line. There are 8 data bits, 11001010 or whatever, and then again the acknowledgement is sent. Finally, there is a stop condition and the data line will go high after the clock. Since an external clock line is used, communication is still faster and more reliable than USART. Remember, USART didn't have a clock to begin with, and while it is slightly slower than SPI, well, okay, because you now do have a clock, but you aren't using the chip select wire, you still send the address, and that's a necessity for I2C. The use of the address signal means up to 1,008 devices can be connected to the same 2 lines, and they'll be able to communicate. Now we understand the basics of hardware communication protocols, and we can start to analyze the logic of the rogue implant. So let's lay our cards out on the table. We've got USART, kind of protocol number 1 we were looking at. You've got SPI, serial program. I got to go look at that one was. Serial peripheral interface, and then I2C, the interchangeable etc. Inter-integrated circuit, and we've sort of increased our capability or bettered our solution with those. USRT did not have a clock. It still used a receive and transmit lines, but the SPI did use a clock. However, when it was trying to communicate with multiple devices, it required the chip select wire. However, moving up to now, I2C, you don't need that chip select wire, you still have a clock, but you will need to go ahead and specify the address of who you want to communicate to every time that you need to send data out. So those are our 3 players on the board, and now we're going to probe the logic of what this rogue implant was doing. It says, after sending this rogue implant to the forensics lab for analysis, the following circuit diagram is uncovered. Based on the diagram, it seems like there is a microprocessor that's connected to this ESP32 chip. Doing some research, we can see that the ESP32 chip allows microprocessors to communicate over Wi-Fi and over mobile networks. So whatever this implant was doing, it was definitely communicating with someone else, something external, something public, and that might be dangerous. It might be nefarious and malicious. So if we can intercept the communication between the microprocessor and the ESP32 chip, we would be able to see what commands and information are being sent. This sounds like the perfect opportunity for our red and blue team to team up. Elf Forensic and Elf Recon are on the job. So the elves realize that these chips are probably using digital communication that can be intercepted with a logic analyzer. Looking at the wires between the chips, we see a black wire connected to a pin called GND. Remember, that's ground, and a red wire connected to a pin called VIN. Now remember, that's, I don't think we explicitly mentioned it in our reading, but that is voltage in, right? That's our power here. I did get 4 years of education in electrical engineering, but I slept through probably all the classes and I don't know anything. Elf Forensic knows from experience that this would be the ground and voltage in wires, respectively, meaning that these wires are used to provide power to the chip. That then leaves the green and purple wires that would be used for data transmission. Seeing that they're connected to the RXO and TXO pins, that's a 0 by the way, not an O, so the receive 0 and transmit 0 pins, Elf Recon can deduce that this refers to the transmit and receive lines of USART communications. Hence, we're pretty sure that the protocol used for communication is USART. Armed with this information, the elves connect the probes of their logic analyzer to the green and purple wires before powering on the implants. Immediately, super fast signals are seen on the analyzer. The elves create a logic data dump from the signals, and McSkitty is asking you to investigate what actually is being transmitted. So now let's go ahead and analyze the logic. In order to analyze the logic data dump, we'll need to use a logic analyzer tool called Soleil. I don't know how you say the Soleil. I'm really out of my element here with this hardware stuff, aren't I? Start the machine attached to this task if you haven't already, and it will open an in-browser Windows machine where all the required tools have already been installed for you. Once the machine is loaded on the desktop, double-click the Logic 2 application. Once loaded, you should see this screen. And there's our Logic 2, little logic analyzer. Let me go ahead and do that. Start this machine attached to this task, which will open up an in-browser Windows machine. I do not quite see my in-browser Windows machine. Can I RDP into this? Or let me go back to the top. Show split view. There it is. Okay, now we are logging in here. I've got the machine pulled up. All right, now Windows is logged in, and we do have this in-browser Windows machine where all the required tools have already been installed. So let's double click on this Logic 2 application. I see that Logic 2.4.2 on the desktop here. Once loaded, you should see this screen, and it'll fire up this Soleil. I'm gonna get like 47 instances of this thing popping up. Oh. Okay, we're going. Yep, got like 3 instances. All right, now our logic analyzer is fired up and loaded. It says, let's import the logic data dump to start our analyzer. Select the open a capture option and select the Santa file that's on the desktop and click open. Okay, so capture, no. We want open a capture in the file menu, or Control O, right? Moving over to my desktop here, let's select that Santa icon. Double click that. Looks like this takes a little bit of time. It was decompressing. Now it's preparing the session. Oh, I do see this device calibration error, but over here in the TryHackMe guide, it says, hey, you can ignore the calibration error pop-up. Okay, so we're good. And once this is loaded, you should be able to see the captures. Looks like it's coming in way over here on the right side. If you hold down left control and use the mouse wheel to zoom out or zoom in, you can click on view and zoom out just as well. You should be able to see the digital signals. All right, well, hey, let's close out of this device calibration error. I'm going to ignore Logic 2's little banner here, and I'm going to hold down the left control key and, ooh, yeah, okay. I can zoom a little bit, drag to zoom. Oh, there we go. Okay, cool. When I was over on channel 1, I'm seeing a little bit better there, or others here. Cool. Okay, so I can click and drag around a little bit. Now what do we have? We see D0 and D1 refer to the digital channels of the 2 lines that were probed. Let's see, what is noted as, okay, so that's D0 and D1 way over here, right beside the channel 0 and channel 1 reference. So that's digital channels. A0 and A1 refer to the analog data from the probers. Hover over your mouse to see the first line on D1, channel 1, and use left control and mouse wheel to zoom in again. You should be able to see the entire signal transfer. What? Do we just zoom? Oh, I don't have a whole lot of room. Can I hide this device thing? Put that away. Yeah, okay, cool. That's better. So I'm currently zoomed out. If I keep zooming in, ooh, look at that. I got the squares. I got the wiggles that go burr. All right, cool. What is very interesting from this screen is that you can see how the analog voltage data corresponds to the digital signal that is seen. Looking at the A1 channel right down here versus the D1 channel, you can see that there are slight breaks in the analog data that have been corrected in the digital channel. Now that we can see the digital signal data, we can look to use our logic analyzer to read the contents of the data. Click on the Analyzers tab to the right. That looks like this little 1F over here. Since we know the protocol is USART, again, from just looking at the chipset, you can see the TX0 and the RX0, just the transmit and receive lines between the ESP32 and the microcontroller. So since we know the protocol is USART, let's look to configure an async serial analyzer for both channel 1 and 0. Let's configure channel 1's analyzer first. If we were true hardware reverse engineers, we first would have to figure out the rate at which this data is being transmitted, as well as the specific configuration, such as parity bits and frames. Again, because USART has all that stuff, right? You needed to determine the baud rate that both devices will communicate on. But to keep this simple, Forensic Elf has already discovered this for us. Huge thanks, super appreciate that, Forensic Elf. Alter your configuration to match the following and click Save. All right, so if I click on this, I think, oh no, the async serial right up here, and there we go, it pops it open. We need the bit rate to be 4800, type in all the wrong stuff. 8 bits for transfer, which is the standard, 1 stop bit, which is the standard, no parity bit, which is the standard, least significant bit sent first, which is the standard, non-inverted, which is the standard, normal, and show protocol results stream. All that's just fine, but we do need to specify the channel. So we can click on that and we'll choose 01 channel 1, which we know is on. Once saved, we can see the data is being analyzed. All right, so let's go ahead and click save. Being analyzed, whoa, look at that. Okay. Click the terminal icon, and we can actually read the data being transmitted. Where is the terminal icon? Oh, it's this thing. Click. Ooh. Okay, so we can see that here. I see an ACK reboot, Command X, and other numbers. We see the initialization sequence of the serial line, and then 3 lines of data being sent. ACK reboot, Command X, 195837, and 9600. This doesn't mean anything yet, since we're only seeing one side of the data. In order to see the other messages, we need to add another analyzer to channel 0. Click the plus icon next to analyzers and then add another async serial analyzer with the same configuration, except using channel 0. Okay, so hit plus up here, add another async serial. We need 4800, all that was just fine. So let's just set this to channel 0, hit save. Good. Okay, that's been created up here. You can see it. And nice, I can see the response in the terminal already. It says, hello, command, please send a security string. Looks like that would be the CMDX 195837. Hello, command, security string is accepted. Please specify the new baud rate. New baud rate of 9600 is accepted. And then the other stuff gets a little bit janky. Because now we're starting to piece together the information. It seems like the microprocessor is establishing a session with the ESP32 device to allow communication to the control server. We can now see the full discussion between these two devices. The processor asks ESP32 to reboot its connection to the control server. ESP32 is happy to oblige, but requests a security code to allow connection to the control server. Once the security code has been transmitted, the ESP32 allows the microprocessor to negotiate a new baud rate to be used for the rest of the communication. Interestingly enough, once this new baud rate is accepted, we cannot read the rest of the output. That makes complete sense, right? Because it's not going to be at the same baud rate that we just defined. A lot of this looks like it's going to be halved in a way, right? We went from 4800 to now 9600. However, since we intercepted at this current baud rate, 4800, we can simply edit our channel 0 analyzer to a new baud rate to read the rest of the communication that was sent. Go make this change and you can get your flag. All right, so let's go into our async serial 1, which we know is the other channel 0 that we were looking at that got us the interesting stuff. Let's go ahead and edit it, and let's change our baud rate to 9600. Hit save on that. Now the rest of the language will not be able to be read, right? Because that baud rate is all muffed up. But at the very, very bottom, you can see it here. THM, hacking hardware is fun. I dig it. All right. And that is our flag. That is the completion of this. The practical portion, however, we need to go ahead and submit our answers here. It says, this is excellent progress. We were able to read the initial communication service between these two devices, that they were used to establish a connection to the control server. Now that we have this information, we can keep monitoring the lines and analyzing the logic to see any messages that might be sent further. Yeah, we can play with the signals here and see what else is going on. So this is pretty slick. This is awesome. We're one step closer to knowing who is responsible for this rogue implant. All right, we got that flag. We are done with the practical portion. Let's see if we can cruise through these answers and test our learning comprehension here. What devices can be used to probe the signals being sent on electrical wires between two devices? Well, we've been using Soleil and Logic 2, right? All of that is to mean it is a logic analyzer, correct? Submit that. Oh no! Do I have that wrong? Am I spelling that wrong? Am I dumb? with an S? Okay. USART is faster than SPI for communication. Yay or nay? No, right? Because SPI uses the clock, and that's like better and stuff. Yeah, we were able to read a little bit about that on how it was able to do those different things, especially with the like chip selector and everything that SPI would be doing. SPI was a greater than communication than USART in some scenarios, right? USART communication uses fewer wires than SPI. That should be no, because you still need because SPI still needs all those other things between the chip select and all, but USART does need transmit and receive, TX and RX, right? So let's go with yay. Okay, dude, I'm cool. USART is faster than I2C for communication. No, not at all. Not that one. Nope. I2C reigns supreme with our three musketeers here. I2C uses more wires than SPI for communication. Yay or nay? No, it shouldn't need to, because it's sending the address. It doesn't need the chip select. Nay. SPI is faster than I2C communication. That is true, because the address will take time to send it with I2C. So yay. Excellent. What is the maximum number of devices that can be connected on a single pair of I2C lines? We got that. That was a 1008. The good old whopping 1008 number there. What is the new baud rate that is negotiated between the microprocessor and the ESP32 chip? Okay, so that's getting back into our practical here. That is not any of the tests are learning from our reading above. They chose, after the reboot sequence and the special command, 9600. Submit that, and there we go. What is the flag that is transmitted once the new baud rate was accepted? Can I paste this in here? No, I think for one thing, I already ate my clipboard. There, nope, it won't let me do it. THM, hacking hardware is fun. All right, once we hit submit, we're gonna be done with this task, which is kind of wild, you know? We spent a little bit of time learning something new. I got to learn something new for sure. I don't know about you, but let's hit submit and done. We did it. We finished day 19. We rolled through some sweet hardware hacking with Wiggles Go Burr, and that is everything that we need to learn about and cover for day 19 hardware hacking. Well, good golly gee, everybody. Hey, I think that's wrapping it up for today's Christmas extravaganza with the TryHackMe Advent of Cyber. Man, I gotta admit, that was kind of cool. I haven't done that before, at least if I have in a very long time, for things that I might have been supposed to be doing in my electrical engineering degree. But that was super slick. Logic 2 is very, very cool in how it was able to put together some of those analyzers for us. I, for one, now know the difference between USART, SPI, and I2C, and can tell some cool stories, you know, hanging around the Christmas tree and the campfire. Campfire? No, the fireplace. That's the one. The thing with the one with the presents and the ornaments all around it. Hey, now I can impress my family telling them about chip selection, how you can select up to 1008 things. Peripheral devices. Thanks so much for hanging out with us, everybody. I hope you had a lot of fun with this one. I know there was a lot of reading, a lot of learning, but you know, sometimes that's very necessary and sweet. TryHackMe was able to give us this interactive lab environment with that practical and application to be able to play with. So, hey, as always, huge kudos, huge thank you to TryHackMe for putting together the TryHackMe Advent of Cyber 4 for 2022. And look, guys, we're only about a week until Christmas or so, right? December 19th. What? We're getting to the end of this thing. It's wild, it's crazy, but we've had a ton of fun, and thank you for being a part of it. I hope you enjoy. I hope you go solve this challenge, and I hope you go solve the rest of the TryHackMe Advent of Cyber challenges, and we'll keep on cruising until the holiday season and then the new year, where we get to have even more fun. Thanks so much, everybody. Hope you enjoyed this video. I love you. I'll see you in the next one.